Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullah. Peace and blessings upon you all. Dear students, today we talk about the AVL tree. Now, the question which comes in the mind is we had the binary tree, we then said binary search tree, then why the heck we have the AVL tree? Okay, let's try to understand this. We had a linked list, we got a start, and then we had a node, then another node, and so on. Now, this was kind of a primitive because we have to search, we have to delete, we have to insert, and for a single linked list or double linked list, the operations to be done uh, takes a lot of time. So we said that we have the beautiful thing what is called as a tree, the tree data structure, which help us in dramatically increasing the efficiency in terms of searching the node, in terms of insertion, deletion, and in terms of doing a lot of operations and a lot of it help us to solve lots and lots of problems. Then we said in a tree that we should have a binary tree. Okay, why? Because it gives us a lot of comfort. You have a node, then you got a one node, you got another node, and so on and so forth. That means at the max you can have a two or one subchild. You cannot have three or more than three, like four or five subchilds. Then it will not give us a, actually it will not benefit us in a computer science. We said if we have a two or lesser than two nodes, and if it has a two, the complete binary tree, it really help us. Okay, say for example we have a couple more nodes to that, and so on. And if you see, if we had here one, two, three, four nodes, so the length of this single linked list was four, right? Now here, for example, we have one, two, three, four, five, six, and seven nodes. For example, if this one has a seven nodes, one, two, three, four, then five, then six, and then seven, and as you could see, the length of this will be the seven. So that means if we have n nodes, the complexity of this will be big O of n. Okay, because n times you have to go somewhere, search something, you have to, in a worst case scenario, you have to go to the n times, okay, to search that particular thing, right? So we want to minimize this thing, we want to make it efficient. That's why we had a binary trees. Okay, and here the maximum height, the from say this is the root, from root to the last node, it was the n times. If we have n nodes, say for example we have the seven nodes or eight nodes, it's the eight, the last node. Okay, if you want to find the last node, you have to go for searching eight times, you have to use eight iterations, then you can reach there and get it. So n, if we have n nodes, we have to go for n times. Okay, so but this tree, when I say the tree structure, this really helps in it. I'm just saying seven nodes. Consider some 2 to the power 10, the huge number. Okay, like 20,000 nodes. Okay, uh, and so on, if you have such things. So we have 20,000 iterations to do to find that, but if you put it in a tree, it will be just 10 or 11 the height of it. If you see here, we got just 1, 2, and 3 at the three locations. If we have 1, 2, 3, 4, 5, 6, 7 nodes. So if we have 7 nodes, for example, so 7 plus 1 is equal to 8, and we know 2 to the power 3 is 8, or in other terms we can write is log to the power 2 to the 8, that is equal to 3. We can write this way in mathematical, in logarithmic terms, like this. That means if you have an 8 nodes, if you do the log of that, you will get 3. So that's why if I have got 8 nodes, the height of this tree is just 3. So the height of this tree is log to the base of 2, whatever the n is, plus 1. So n was 7, 7 plus 1 is 8. So log to the base 2 of 8 is 3. This is like, if you got a 2 to the power 4 is 16, I can write in logarithms like this: log to the base 2, the same 2, of 16 is equal to 4, whatever the raised power comes in. तो logarithm में ऐसे लिखते हैं, ठीक है ना? So that means if I have a 16 nodes in a single linked list, you have to have a 16, the length will be 16. So if you have find the 16th of element, you have to go for 16 iterations to find it. So consider 20,000 nodes or 10,000 nodes. So it will be the huge thing, right? Say for example we have 1048576, this much of nodes, around 10 lakh nodes. Okay, so what is the length of this linked list? The linked list will be same, it will be 10 lakh for 48,576. And if the last node you have to search, and you have to go for 10 lakh 48,576 iterations, that's going to be very huge. But if you arrange the same nodes in case of your binary tree, okay, so because we know 2 to the power 20 is this number 1048576, so at the max of this height of this tree will be log to the base of 2 of this number 1048576, that is my total number of nodes, will be equal to 20. So only height will be just 20. So such big nodes, you can compress them in the height of 20. So that means your computation will be very simple. So that will be big O of not n, rather this will be big O of log n. So from big O of n to the big O of log n, because you have reduced this number to just 20. This number was 2 to the power 20, the total number of nodes, and it has reduced it to 20, just 20. So see how efficient our binary trees are. Then we said that okay, if we arrange the binary search binary tree and put it the things, but if we do not put it in the nodes in some order, then searching will not be better. So we said then okay, do it for the binary search tree. From binary tree, b tree, or not b tree, it's a binary tree. Okay, we created binary search trees. Okay, in a binary search tree, what we do is we just arrange the nodes such that searching becomes easy. Rest the concept is same. This length, this the breadth or depth of this tree, or the length of this tree is highly reduced. That reduces the computation, that reduces the searching time, and insertion and deletion becomes easy. But searching won't be easy if we do not arrange the nodes in a search order. That is, we said, hey, if it is 40 for example, and if any node comes in which is lesser than 40, it should go to the left. Okay, and if any node comes in which is greater than 40, it should go to the right. If anything comes less than, say for example, the 5 comes in, now 5 is less than 40, should we go to the left? 5 is less than 10, so it should go to the left of this. Okay, now say for example 15 comes in, the 15 will be lesser than 40, so go to the left. Now 15 greater than 10, go to the right, so 15 will be here. Same way 50, say 45 comes in, 45 is greater than 40, so go to the right. Now 45 is less than 50, it will be here. And if it is 55, it will be here. Now if you arrange your nodes in this manner, okay, where you have the bigger one on the, that is 40, okay, on the top, and if something is lesser it goes to the left, and if something is greater than 40 it goes to the right. So this subtree will have everything greater than 40, and this subtree will have everything lesser than 40. So if you want to find, say for example 45, okay, in first iteration, okay, say for example you have like 10 lakh 4,805.76 nodes. So in a first iteration, if something is what you want to find is for example 45, okay, we know it has to be in the right of the tree, so you do not have to search the left tree. This whole computation of finding these nodes, okay, left tree, is just reduced. You don't have to do that. So if it is a 10 lakh 48,000 something, so 5 lakh 28,000 something nodes, you do not have to search at all, right? You do not have to search because it cannot be in here, it has to be in this. Now in the second iteration, if you want to find 45, it cannot be on this subtree, it has to be on this subtree only. Okay, if I see this particular tree where we have 1 2 3 4 5 6 7 nodes, I want to find 45. In a first go I will say 45 is greater than 40, it has to be here. Now it has been less than 50, it has to be here. So only 2 iterations it will take. But if it is in a linked list form and I got 1, 2, 3, 4, 5, 6, 7 nodes, so it will take 7 iterations at least if it is a worst case, okay, to find it. Do you understand? Not at least, at max I'm saying, because if it is a worst case, you are finding the last node. Okay, in this case, if you want to find the last node, it will take just 2 iterations. First iteration, if for example 55 you want to find 55, 40 se bada hai, it is greater than 40, so it has to be in a right tree. Okay, it cannot be in a left tree. Now 55, it is greater than 50, it has to be right of the left, and you bingo, you got it. So same is if you got a 48,576 nodes, for example, at the max it will take is a 20 turns. So 20 iterations, worst case, last node you want to find. At the max, the 20 iterations will take. But if it is like a linked list like this, it will take you 10 lakh 48,576 iterations to find that, and so on. So it is really tough in case of linked list, and the competition becomes so easy if you arrange the things in a tree. Okay, so now we say binary tree, and then we say binary search tree. The binary search tree itself is a binary tree. Okay, but with the additional property that elements are arranged in this fashion, that if something is lesser than the root, it will go to the left subtree. If something is greater than the root, it will go to the right subtree. Perfect. Okay, but life is not that easy. We think, okay, we got nice solutions here, but life always doesn't give you the apples. What I mean is, if you got, say for example, the things which comes up here is like this, the nodes which comes up here is like this: 40, 41, 42, 43, 44, 45, 46, and so on. So what will happen in a binary search tree? We'll put up the 40 here. Well, what is next? 41 is greater than 40, it has to be on the right subtree. Then comes 42. 42 has to be the right of 40 as well as right of 41. 43, it has to be right of here. It has to be 44 right of here. 45 right of here. 46 right of here. And it becomes, as you could see here, what is called the right skived. It's a worst case scenario, because life can throw you the worst case. And you see here the advantages which we are talking about, कि भाई साहब अगर आपको, if you have a 10 lakh 48,000 this much of nodes, you will just have a depth of 20. But in this case, if you have a 10 lakh nodes, it will be 10 lakh, the height of the tree will be 10 lakh, not that 20 log n. It will not be log n, rather it is back to n. So we are back to the square one, we are back to the zero. I mean, जहां से हम शुरू किया था हम वहीं पहुंच गए. जो n, इसमें n node, height इसकी n होगी. So if you have 10 lakh nodes, the height will be 10 lakh, not that 20 and all that. Not log n. Okay, it will not be log n. To the base 2 पता ही होता है. Okay, it will not be, because it is right skived. As you could see, it's like a single linked list. So it's like you have a snake and ladders, that you reached advantage point of 99 and the snake bited you and you're back to the zero. It's like that. क्योंकि जो फायदा हमने किया था, जो the things we have gained using the binary search tree, okay, firstly from the binary tree, then from the binary search tree, it's of no use, because we are getting the single linked list back here in my right skived tree. Same will happen in the worst case if the elements come all which are lesser than the root. So they will all go to the left, 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 left. Right? So then we say, hey, bro, stop. We got to do something more. We said we had a linked list, right? The story goes like this. We said we had a one second. Excuse me. We said we had a linked list, LL, linked list. Then we said, no, we can't do this. We need tree and a tree. Okay. Then we said, no, not any tree. Use a binary tree, which is very helpful for us. Okay. Because it gets you from the log n to the log n, right? You understand log n to log n? N means if you have a 20 nodes, the in a single linked list, the length will be 20. But in our binary tree, the length will be log of that, whatever that is. Okay, say for example, if we got a 24 nodes, okay, if we got for example 32 nodes, Okay, log of 32 to the base 232, that's 5. You have only 5 depth. Height of the tree in a binary tree will be only 5 if you have 32 nodes, right? So it dramatically, changes that. Like I said, if you have got a 10,048 10,48,576 nodes, the height will be only 20. That is log n. Log of 10,048,576, that is 20 on, because 2 raised power 20 is this much. Okay. Okay, now we said binary tree, yeah, it gets us from the n to the log n. Okay, but then we need a good piece of searching. So for that we said we need binary search tree. Okay, the binary search tree, which will help us in searching, dramatically decreasing the search time, because the root nodes are arranged in a search sequence where we can use, like we had a binary search in our arrays. Here it's also like a binary search, where that's why we say binary search tree. Okay, because the elements which are greater than the root on a right subtree, elements which are lesser than will be on a left subtree. So if you are searching something, the bigger than the, or the smaller than the root, then if it is smaller than the root, I know it has to be on a left subtree, so I do not have to search any right subtree. Okay, search becomes so easy and so fast. But again, if the data comes like this, when it's a right skewed and left skewed, again we've gone back to the linked list kind of a thing, because it's again linear, not non-linear. Because we have a non-linear data structures here, but when you say tree, but now we get back to the linear and back to those problems again, because it's right skewed. Okay, the tree is arranged in such a manner. So here comes the concept of AVL tree, which does what? Which does the balancing. Now AVL tree is the example of binary search tree. AVL tree at any point of time will be the binary search tree itself. Binary search tree in itself will be all the time binary tree. Okay, so if it is a binary tree, for example, binary search tree, all binary search trees are the binary trees, and all AVL trees, all the binary search trees. That means AVL tree, you do balancing if something happens like this. Okay, it is trying to get skewed, you have to do the balancing such that this structure remains all the time. This structure, the 40 50, this kind of a binary search tree structure, the structure of binary search tree stays there, even though the data is worst case or whatever case it is. But still, the balancing, you what you will do is, you will do the balancing. Okay, how you will do the balancing? By rotation. So this is what we do in our AVL tree. We balance any, if the skewness comes in, we balance that and make it binary search tree, force it to become binary search tree. And how you do it? By rotation, such that our advantages of binary search tree, of searching, deletion and everything, it stays there, even though it's a worst case scenario like this. Okay, so let us see how we balance it and how we rotate. Okay, that we do in our next lecture. Okay, uh, so stay tuned for the next lecture, where we see how we do this balancing and rotation.